Alright, welcome back to Meteorology 101. In this video, we're going to talk about air temperature. So, the last two videos, I'm kind of doing a little series here on basically basic meteorology. Not getting too deep into stuff, but getting into a pretty decent discussion. We're talking about layers of the atmosphere in the first one, the second one, incoming solar radiation, temperatures. Now we're still kind of on temperature. Temperature is one of the most the biggest things that affects weather. So as you get a cold air mass, warm air mass, anything moves into the region, that based on the temperature of that air mass, moisture obviously too, but temperature is a big playing factor of how much moisture an air mass can hold just based on temperature. We're going to cover how the temperature varies daily, monthly, yearly. Pick out a couple locations on the same latitude, compare those, and then controls of temperature, organization of temperature data, a little bit of that, and then measuring air temperature and what instruments are used. Obviously a thermometer. So different types of thermometers is what we're going to basically cover on that. So the daily diurnal temperature variations, the daily cycle of temperature is very much like seasonal cycle. So warm begins in the morning, we call that spring. Hot in the afternoon, say that's summer. Cooling in the evening, that's fall. And coolest late in the evening, early morning, that's winter. So you'll see your minimum temperatures, early in the morning usually. Can't happen overnight. That all depends on, air masses, frontal passage. If you take frontal passage overnight, before late in the day or overnight, and then a colder air mass comes through, and you can have your minimum temperatures either early in the morning, late at night. That's all that stuff can change based on certain conditions. And just like seasons, due to differential between incoming solar radiation and outgoing Earth radiation. So any solar radiation from the sun comes in, the Earth absorbs it, and then re-emits the radiation. The difference is there. That's going to be, changes of temperature throughout the day. And then based on cloud cover and several other factors. So, daytime warming. As we covered earlier, solar radiation heats the Earth's surface, which in turn heats the air by conduction. So in the last video we talked about conduction, advection, different ways. Like conduction is the air sits on the Earth emits radiation, heats that air mass above it. So that is your conduction, like putting a pan on a hot stove, then the molecules transfer the heat, the molecules start moving in the metal, and that transfers that heat through the metal. That's done by conduction. So how this heat is distributed depends greatly on the wind. So calm wind, hot air remains near the surface. So the hot air being emitted from the Earth, heating that air, there's nothing to move it around, so the wind's not going to, it will raise a little bit, but not much. Thermals are small and don't bring much hot air up, so you're not getting a lot of heating, a lift from that without help from the wind. Temperatures 5 to 6 feet above the ground can be 30 degrees colder, and this is why the temperature measurements are not taken at the surface, also in the shade or over grass. So if you have a weather station, or the weather stations have the National Weather Service, they have ASOS's, automated surface observation systems, that if you have a weather station that you purchase, they want you to put that about 33 feet up. So that's typically, like I said, 5 to 6 feet above the ground can be 30 degrees colder. So they want to make sure you're close enough to the surface to get an accurate reading, but not so close to the surface where you're catching that emissions from the Earth with the outgoing solar radiation from the Earth, changing that temperature. So daytime warming, we're also on so the air decreases with temperature with height. Out the higher the altitude, the colder it gets. There's a average lapse rate is 6.5 degrees per 1,000 meters. So every 1,000 meters you go up, you're averaging a drop in 6.5 degrees. The only reason I put this picture on here is that thermo shelter. It's a lot of weather stations have those, and they store their thermometers. So basically, they're not taking a thermometer from the indoors and taking it outdoors and then trying to get a good reading on temperature. They sit out there in that air, in that shaded area, in that thermo shelter, and you have two thermometers right next to each other on a sling psychrometer. I don't know if you've ever seen a sling psychrometer. I didn't put a picture on here. I should have. Two thermometers. One of them has a little sock on it, and they wet that with water to get the wet bulb temperature. So then they can get a more accurate reading on temperature dew point. And they actually take this thing, they sling it around in a circle, they spin it like a propeller for about 30 seconds, 20-30 seconds, and then they get a pretty accurate reading on the temperature in the wet bulb. On a windy day, temperature does not change as much with height. Pretty much the wind is just pretty much mixing that temperature, mixing the air pretty much all together, so the temperature stays pretty steady with height at that point. The wind creates turbulent eddies, which transfer heat from near the surface upward and cool air from above. So like I said, it's just basically mixing all that air up, and then you get like basically one temperature, pretty steady up into, not too far up in the upper levels, but I mean, because realistically, temperature does decrease with height in our atmosphere. So to change that, if you had a pretty strong winds, I mean, the temperatures can stay pretty close, but you're still going to get a steady decrease in temperature with height. I guess that's what I'm trying to say there. Anyway, that graph, if you look at a calm afternoon, you get that ramp of a pretty good drop in temperature with height, and then it steadies off. And then if it's a windy afternoon, it's just a steady drop. It's a slighter steady drop just because of that mixing. Maximum daily temperature. The sun is highest at noon. So why do we get our maximum daily temperature? Usually occur around 4 p.m. or so, and it has to do with the absorption and emission. The incoming solar radiation, the absorption of that radiation, and then the emission of that radiation based on what surface and how much is being emitted versus how much is being absorbed if there's warming occurring or cooling occurring. And when do we have the warming? Warming is like, so when you have greater absorption than you do emission. So if you're taking in more incoming solar radiation than you're emitting out, then you get hotter. So that goes for the body, that goes for anything, a rock, any object whatsoever. So and usually that's the case up until 4 p.m. There is more absorption going on up until 4 p.m. until that's when the cooling starts, right after 4. So you got warming all the way up to that point. So thermal lag, that's basically the reason. Incoming solar radiation is maximum at noon, but the incoming solar radiation is greater than outgoing radiation until late afternoon. And warming continues until outgoing becomes greater than incoming. So about 4 p.m. is when that change starts. Now you have less incoming solar radiation than you do outgoing, and then you start to cool off at that point. So the thermal lag is basically, think of it like incoming solar radiation from the sun hits the earth. You got all that incoming solar radiation. The earth's still rotating and moving around the sun. So now you have, by the time that incoming solar radiation meets its maximum incoming to the point that it cools, that the earth is rotated and it starts to cool, your maximum temperature is later in the day. So I hope that kind of clears it up a little bit. Incoming solar radiation, strong, and then just slowly gets weaker, but it's still strong incoming solar radiation, absorption until it finally reaches that threshold where it can't absorb anymore. There's no more to absorb because now the earth is already rotated, the sun's too far away, and then it starts emitting more radiation than it's absorbing, so the cooling starts. So that's your thermal lag. Alright, so your maximum temperature is at 4 p.m. on average. But it can occur at other times based on several factors: clouds, bodies of water, sea breezes, the good example. So clouds is say the greenhouse effect. If you had a clear morning, say clear up till 10 o'clock noon, and a lot of incoming solar radiation, sun just bright as it can be, heating up the air, and then all of a sudden the front approaches, you got clouds. There's clouds just start to build up from the heating. You get the cloud cover, then all of a sudden you have less incoming solar radiation. Then your maximum temperature can be earlier in the day. So same thing with at nighttime. If you have a warm front pass, your maximum temperature can be later in the day after that frontal passage. You get into the warm sector of that low pressure system, that frontal, the head of that frontal boundary, the cold front. Then behind the warm front, that's where your warm sector is. Then you can have a higher temperature, maximum temperature at any given time at that point, whenever that time of that frontal passage is. Bodies of water, so air over water is generally cooler than air over land during the summer. So we talked about this in one of the last videos. I think the last video, that the land heats and cools 5 times faster than water. So when you get that heating, the air is colder over the water. You get the heating over the land, and then that creates a little bit lower pressure with heating over the land faster than the air over the water. So then the air over the water rushes in and takes up that lower pressure, so that creates a sea breeze, and that can cause a drop in temperature too. So 4 p.m. is the maximum. We're going to talk about that. That's the average time maximum temperature occurs. So, okay, large storms and their fronts. We talked about the warm fronts, frontal passage. Now, you could have just maximum temperature early in the morning. Cold front comes through, passes early in the morning, and then your maximum temperature is early that morning, and the cold air mass hits you, and then you're just cooling off the rest of the day. So we see that happen quite a bit too. Same thing with the warm fronts. You get a warm front pass, then you can have that maximum temperature hit right away. And then as the day goes, if it's cloudy, it can just continue, that air mass can continue to cool, or if it's not cloudy, continue to heat up. But the passage of the warm front or the cold front can definitely change the time of day that you get your minimax temperatures. I'm sure you've seen it late in the day, early in the mornings. Typically early and first thing in the morning, right before sunrise, is when you get your minimum temperature. That's kind of average. All right, factors influencing maximum temperature. So what influences the maximum temperature is the soil type. Some types of soil absorb more energy due to color, texture, or albedo. We talked about that in the last video. Say like a smooth dirt will absorb and emit more than, or will emit, I guess, more than like a rough dirt. That would just absorb that radiation and then not emit so much. Or maybe create a lot of shadows over a rough ground. You could think of it like that, and that keeps that ground cooler too. So texture, has a lot to do with it. Moisture, wet soil heats up slower, and some energy goes into evaporation. So anytime anything evaporates, that's a cooling process. So evaporational cooling, that'll affect your maximum temperature. Vegetation, if you have a lot of trees, once again, evaporation. Because trees do transpire, that's part of the water process. And then clouds, humidity, and haze. So any reflection from the incoming solar radiation hits haze, clouds, and then moisture, a lot of moisture in the air, then that reflects that back into the space, and then you have less incoming solar radiation, so that will affect your maximum temperature also. So factors influencing maximum temperature also continued. Ideally, to get the hottest daytime temperature, soil, which is a good absorber, sand for one, dry soil, no vegetation, no moisture in the air. That's the way you're going to get the hottest hottest conditions, and that obviously describes a desert. No vegetation, dry, sandy, in the southwest. So here are the comparisons between two cities, Atlanta and Phoenix, both in the same latitude, same amount of incoming solar radiation. But Atlanta is humid, cloudy, lots of trees, and average in July of 87 degrees. So with the trees, that's going to be, they absorb the moisture, transpire, let off the moisture, basically evaporation, and then you get the cooling. Temperatures are cooled to the dew point, and that can, create saturation and, create clouds. So now you got more clouds. Phoenix, you don't have that. You get dry, it's clear, less trees, and your average is 105 degrees. So that's basically, we'll show you just on the two different surfaces, two different types of soils, and what how that affects the maximum temperatures and average maximum temperatures on the same latitude. Nighttime cooling, around 4 p.m. the Earth starts losing more incoming radiation energy than it gains in solar energy. So once 4 o'clock hits, that's when all the incoming solar radiation pretty much stops, and then you have more outgoing solar radiation. So that's your that's why you have the cooling process. So both the air and the Earth cool by radiating IR energy, and that's radiational cooling. So the Earth radiates at a greater rate, so it cools faster. So it radiates faster than it absorbs, so it cools off faster than it heats up. We talked about land. Land actually heats and cools 5 times faster than water, so that's a big factor. Earth is a big player there. Just as air near the surface warms by conduction during the day, it cools by conduction at night. So you no longer have incoming solar radiation. You have outgoing solar radiation emitting from the Earth, and then it cools. That air cools, and by conduction, it cools at night faster than it would heat up during the day. By late evening, early morning, air at the surface is cooler than the air above. So by late evening, early morning, air at the surface is cooler than the air above. So you have the radiational cooling, cooled by conduction. Initially, you have that cold layer at the surface, and what you'll see a lot of times on flatter in the plains or flatter grounds, like mainly on the East Coast. I forecasted on the East Coast, and I see it almost every morning through the summers. The cooling would happen, and then the surface air temperature, would cool pretty quick, and then you would actually have an increase in temperature with height. So you had an inversion. So once that inversion set up, then there was only 2 ways to break an inversion. That was either heat the surface temperature or cool the air in the upper levels. So you had to cool the air in the upper levels, bring that temperature down to equal to the temperature of the surface. That would break the inversion, or heat that surface. But if you had cloud cover, which typically, if you had an inversion, you had the moisture present, because we were pretty close to the ocean, had a lot of inlets and rivers around us. So we had the available moisture. You'd have the radiational cooling, and then you get any kind of just a light wind with any moisture advection that would come in, and then you get a radiational fog, and then that fog would, create a layer under that inversion, and then when the sun did rise, it would, the sun couldn't hit the surface and heat surface temperature up. So it would. Basically, you'd have to wait till the upper levels cooled off to the surface temperature to break that inversion to dissipate that fog. So, I'm talking about temperature, so I'm just, I didn't want to get too deep into that. But all right, nighttime cooling, radiational inversion. We just talked about that. The increase in temperature with height, the radiational cooling at the surface of the Earth, and it's also called a nocturnal inversion. So, like I said, if you look at this chart. Let me get my mouse over here. You can see got an increase in temperature with height. Typically on a Scuti chart in our atmosphere, you'll have the decrease in temperature with height. The curve will go this way. to a decrease. But so since that radiational cooling took place fairly quick, then that all of a sudden, the temperature of the air is over here, it's up. It's still cold, but the cooling of the surface by conduction with the air at the surface, then all of a sudden, boom, that temperature just drops. And then this air up here couldn't cool off that fast. So now you got the temperature to increase with height, and then that is your inversion. So anything below this inversion, where that temperature break is. So in this case, it's pretty cold, 30 degrees or 31, 32 degrees there. This temperature that's about 40 degrees would actually have to drop to say 32 degrees, and then that would give you a equal temperature, with height, and then that would break the inversion, and then you can have the incoming solar radiation. The fog would basically just dissipate or rise, they call it, but it just basically dissipates. Now you can have all that wind in the upper air. The upper layers, you got even colder air, because this inversion temperature increases with height and then begins to decrease with height in the upper levels. So now you bring this temperature back down to that surface temperature, you break the inversion, all this cold air up in the upper levels will come rushing down, and then that just creates a mixing, and too much mixing for the fog to handle, so it just dissipates the fog. Because fog requires moisture, and then light winds. You can't have any wind with fog. Basically anything less than 6 knots anyway. Factors affecting minimum temperature: wind, light wind, colder temperatures, strong wind, warmer temperatures. So wind causes coldest air near the surface to mix with warmer air above. So less chance of an inversion. So you're not, anytime it's windy, you don't have that chance of that inversion because you have too much mixing going on in your temperatures. Warmer. The surface air and the upper air is basically going to mix. So the colder air in the surface mix with that warmer air, and it just averages out. So you're not really, creating a increase in temperature with height. So you don't get your inversion. And length of night, longer nights, more time for radiational cooling. So all that incoming solar radiation during the day, if you got like in winter time, we have our shortest days in December, and you have incoming solar radiation, so it'll be warmer during the day, and then you got those long nights, and it's dark at 5 o'clock. Sun doesn't rise till 7:30, 8 o'clock the next morning. Then you have a lot of time for radiational cooling there. So then that's a major impact on your minimum temperature. So it's going to be, that's where you get those cold, brisk mornings. Moisture and clouds absorb incoming radiation and emit radiation back toward the earth, and it's warming. So if the air is moist, we get dew. Condensation is a release of latent heat, and that's a warming process. We said evaporation is a cooling process, condensation is a warming process. So moisture and clouds, that plays a big it's a big factor on the minimum temperature too, because if you got like we talked about, the greenhouse effect, if you got clouds keeping that outgoing radiation from going out to space, it bounces back off the clouds, reflects back down, and then that keeps us warmer overnight. So, and then terrain, cold air is more dense, heavy than warm air, so it moves down slopes into valleys, and it's called cold air drainage. So that typically in the fall, you get that cold air drops down into the valleys and get that drainage. And if you got the moisture available, as that cold air goes down the slopes into the valleys, then it can create a little bit of mixing that you need, bring that moisture up, and then cool those temperatures, surface temperatures in the valley pretty quick. Cool that temperature to the dew point, and then you'll get a fog layer, and then that fog will just sit in the valley until the sun comes up, and then finally heats that up to dissipate the fog. So you get a lot of valley fog from that. All right, controls of temperature. These are the main factors that causes variations in temperature from one place to another. Latitude. We talked about that actually with Atlanta and Phoenix, how they were on the same latitude, but we had different temperatures there, and that was just based on the soil content. Two different types of surface. Now this one is latitude, so obviously you go north and it's colder. So you got more incoming solar radiation near the tropics than you do to the poles. I actually talked about that in the last video. It was the angle of the sun hitting the earth and the incoming solar radiation closer to the equator, the more incoming solar radiation than at the poles. And then your elevation, as you know that you climb a mountain, as you go up in elevation, your temperature decreases in the troposphere. You know, once you get in the stratosphere, then you get an increased temperature of height. You got a stable layer above us. So it's always kind of like there's a transition between them two, but there's always kind of like an inversion above us, you know, way up in the atmosphere that keeps all of our weather down here. And any thunderstorms that go up to the tropopause, then that's pretty much where the clouds stop. And then unless you got a strong enough updraft that can push past that stable layer, that tropopause, then you get the overshooting tops and those cumulonimbus clouds. So temperature decreases with height. And that's what that is typical for the troposphere, unless you have an inversion present at the surface. And, you know, that can only go. That typically an inversion at the surface go up to about 1,000, 2,000 feet. As the land and water distribution, different heating properties. What we talked about before was land heats and cools 5 times faster than water. So that's where during the daytime you get the land that heats up. The water doesn't heat up as fast. So now you have a little bit of like a low pressure system, sort of. You know, there's thermals that go up, and then that cold air rushes in to replace that, and that is your sea breeze. Specific heat is the amount of energy needed to raise the temperature of 1 gram of a substance by 1 degree Celsius. Is the definition of specific heat. So water has a higher specific heat than land. It takes more energy to rise its temperature, and so in the summer, land gets hotter than water, and in the winter, land gets colder than water. So, like I said, land heats and cools 5 times faster than water. So you're, you know, at nighttime, even at nighttime, you can get, you know, the land cools faster, and then that will create a little bit of a higher pressure because it's colder air over the land, and then that will rush out to sea, and that will create a land breeze. So it works both ways between a land breeze and a sea breeze. Ocean currents. So on the east coast of continents, warm currents flow to the north, and then west coast of continents, cold currents flow to the south. So coastal cities in the west coast are likely to have lower summertime temperatures. So you got all that cold air coming from the north going down. And like an example is San Francisco. It's pretty cool, sometimes cold in the summer due to the cool Pacific water. So when you got cold water being carried from the north through the currents, the land heats up, and then that even colder water, the air off that colder water conducts with the air, cools it even more, and then that rushes in, and that would definitely cause colder temperatures. So controls of temperature. January, large change in temperature from tropics to the poles. We know that, north and south, incoming solar radiation. And then lines of equal temperature called isotherms. That's how they're determined on interpreted on a weather map. And then colder over land, warmer over water. Alright, controls of temperature in July. Less change in temperature from tropics to the poles. Actually, let's go back one slide and look at this real quick. If you look at this graphic, it's like almost a world map. But if you look at that in January, what do we got here over the United States? We got the long wave trough. So you got colder, it's colder over land, warmer over water. You got ridging over the water. These are temperature lines here. So, you know, cold air mass over the Arctic, over Canada, continental polar air mass pushes south, and then that pushes that north-south temperature gradient south along with it, and then the jet stream drops to the south to get that troughing over the eastern United States, ridging over the west. I mean, you can put it pushes through, and then you'll have ridging over the east coast too. So, but that's your jet stream sinks way further south in January. All right, in July, less change in temperature, tropic to the poles, small temperature gradient. Like I said, look at the isotherms, how far apart they are. It's over the United States. You got the ridging over the west coast there. Really not much change over the east coast, and then a slight troughing over the Atlantic, but warmer over land. The cold air mass over the Arctic polar high or continental polar, the Arctic air mass to the north, and then continental polar air mass all stays up to the north. You have more heating at the equator, and just north of the equator. That's why our summers are in July, and it's winter in the southern hemisphere in July for Australia. Anything south of the equator. So that's why it's reversed based on the tilt of the Earth. All right, so organization of temperature data. I rearrange air temperature data in two main ways, and that is averages and ranges. So the temperature is going to range from this to this. We're 4 degrees above average. So the average temperature this time of year is this. That's what you always hear. So we're always hearing that average temperature, and then a daily range. Okay, based on what the minimum temperature was and the maximum temperature. So which one of these tells you more about the temperature of any given area? I mean, both of them really, I would think, because what's your average temperature for that area, or average temperature for this area, that tells you about temperature for a given area. Also, the daily range. I mean, you look at temperatures in Ohio. We have a 10-degree, 20-degree daily range. Between minimum and maximum temperatures versus in the desert in the southwest, your ranges are going to be, could be up to 50-degree difference. So that can get tell you about more about temperature in any given area. So I would say both. All right, the daily mean temperature, say in a desert town versus a coastal town, 80 degrees. 80 degrees on a daily mean. Low temp 55, low temp in your coastal town 70, high temp 105 in the desert, 90 degrees in a coastal town. So you look at same mean daily temperature but very different weather. So you're looking at in the southwest 105 degrees versus a coastal town at 90 degrees. And then your low temperature 55 versus 70, but you look at a 50-degree difference there, your 20-degree difference there at the coastal town. So that shows you the difference. What you could tell, like I said in the last slide, was both of those will give you the idea of what part of the country you're in. All right, organization of temperature data, and at any location, the difference in temperatures between the coldest and the warmest months is called the annual range of temperature, and the largest annual range of temperature occurs over land, and that's just because land heats and cools way faster than water, so water is not going to change that much. You're not going to get a big temperature range over water, so that's always going to be over land. An area is a large annual changes in solar radiation. So if you're in a cloudy area or an area that gets fog all the time, here's an example: a near Arctic Circle with 112 degrees Fahrenheit. I don't know what that is. There's large annual changes. Okay, so the 112 degree temperature change over near the Arctic Circle is 112 degrees on an annual temperature change. Smallest annual range of temperature over water, like I said, the heating and cooling of the water versus the land. And the tropics, you're going to get a small annual range of temperature, because the tropics, the sun the Earth rotates around the sun, and the sun's always along the equator. It might be a little bit north or south on that variance, depending on the tilt of the Earth, but your variance ain't going to be that much. So that tilt of the Earth, when you got the Arctic Circle, facing away from the sun, then you're going to get a heck of a drop of temperature there. Islands near the equator, 1 to 2 degrees Fahrenheit from warmest to coldest months. So there's really not that big of a temperature variance, between the warmest and coldest months on the islands. As well as a lot of your islands, they'll stay pretty much the same temperature year round. You can get that quite a bit. All right. The average mean annual temperature doesn't tell us much without the annual range of temperature. Richmond and San Francisco have the same mean temperature, but climates are very different. So you look at Richmond, Virginia versus San Francisco, you definitely got a different, two different types of weather. And then water moderates temperature in San Francisco. So like we talked about before, was the cold currents coming from the north, and then creating those land breezes, and then winds off the mountains. The cold air dropping out of the mountains, stuff like that. That can always cause those temperatures in San Francisco. The weather in San Francisco will be way different than Richmond. Air temps and human comfort. Definition of wind chill factor: how cold we feel due to temperature and wind. Why do we feel colder when the wind blows? The conduction warms the air near our skin. So as we radiate that emit that radiation, we're warming that air, and then when the wind blows, it blows that hot air away from us, so we feel cooler. Moves more hot, warm air. So the more heat from the body is used to warm the colder air, the faster the wind, the faster the loss of the body heat. So wind chill factor is just how cold it feels outside. It's not how it's going to affect your car in the wintertime. No inanimate object is affected by the wind chill factor. Only humans is how cold it feels outside. Alright, so air temperature and human comfort also continued. What about cold and moisture? We feel colder, when it's also wet outside. Well, why? The water conducts heat better than air, and it can cause hypothermia, a big problem for ill-prepared hikers in the mountains. So, basically, water dissipates the heat a lot faster than air. If you're in the water, you're wet, and you got the wind blowing on you, you're going to be freezing compared to if you're dry. So you just get out of the swimming pool right in the middle of summer, you're definitely cooler as soon as you get out of that pool. All right, measuring air temperature. Thermometers, how do they work? They don't measure the temperature directly, rather than the effective temperature on different substances. Say water, mercury, alcohol, metal, etc. So most common thermometers are called liquid in glass thermometers. The liquid is usually alcohol, if it's red, or mercury. So a lot of your thermometers today are red, so that's alcohol. Used to make them, mercury is probably more accurate, but they don't. I mean, they still make them, but I don't think they're kind of readily available, just because mercury is basically a poison. So if you break one of them, you're supposed to call hazmat and have that stuff cleaned up. So just something to keep in mind. Maximum thermometer uses mercury, and most important feature is the constriction. So basically, as this thing heats up, that mercury is forced through the bore, and through that constriction, it can rise, but it can't drop back down into that constriction. So actually, back in the day, I remember going to the doctor, and they'd always shake their thermometer. So when they pick that thermometer up, they'd shake it. I think what they were doing was pushing that mercury back to the bottom of that thermometer. So when they took your temperature and they got that max reading, they had to use a maximum thermometer, because if they pulled that thermometer out of your mouth And just the transfer from directly out of your mouth to them being able to get a point they can read it, that temperature's already dropped, probably a few degrees. So with the maximum thermometer, it wouldn't drop. They'd have to shake them to reset them. Then they take your temperature and they can pull it out. And then as they're looking for to be able to see that line, they didn't have to worry about it losing any, temperature and giving them a false reading. So the minimum thermometer that uses alcohol, because alcohol is a lower freezing point than mercury. And the most important feature is the index, and that's forced down the bore but not back up. So as this index moves down through that bore, then it won't rise back up. So that obviously gives you the minimum temperature for that day. And then the bimetallic thermometer measured by expansion of brass, and this is what used in most thermostats. So like in the old mechanical thermostats, you had a big winding, a brass winding that would heat up, and when it heated up and cooled, expanded and contracted pretty quickly, and that would change that needle on your thermostat, and then that would make or break those contacts inside that thermostat to kick your heater air on. So this one here, it's kind of like you have the amplifying levers that expose the metallic strip, so that metallic strip has to be exposed to the air to check the temperature, and then the amplifying levers that as the metallic strip contracts or expands, it can't move that needle by itself and stay very accurate, so it uses those amplifying levers to help move that needle in a steady pattern. That way when the temperature changes, you get that steady flow. Like on this one here, you got like the ink on the roll, that would give it keep that steady, so it wasn't jittering all over the place. Basically your analog thermometers today with the needle just goes up and down. That's basically your coil inside there, and then that would as that expands, and the needle would move to a higher temperature. That's the only really main example now we use with those thermometers or temperature gauges with the actual gauge. So alright, that pretty much does it for this video. Went a little bit longer than I thought it was. My next video, not part of this series, but I think we'll build some pressure charts. We'll show you some pressure systems, isotherms, isobars, break down the makings of weather charts. Just so subscribe to this channel, stay tuned, get the notifications, and that way you can keep up with the videos. Like I said before, if you didn't go back and watch some of the prior videos of this series, I'll actually create a playlist on my YouTube channel, so we can keep these separate from the rest. Alright, so thanks for watching, and please subscribe.